This is the video for section 8.1 on arc length, and this is the first section of our new chapter, chapter 8, further applications of integration. So the idea for this chapter is we're going to look at more applications of the notions that we learned for integration, right? So we've already seen the applications for area and volume and work. And now in the next couple of videos we're going to see some more applications. And the first of these has to do with talking about the length of a curve. And I'm not going to say a tremendous amount about the derivation for the formula. I do want to say a couple of things though. And the first of those is that when you do the simplest curve, which is a line segment between 2 points, say x0, y0, and x1, y1, so I'm looking at the line segment between those 2 points. The length of that line segment is given by the distance formula. So that's the square root of the difference of the x values squared plus the difference of the y values squared. And this is essentially a consequence of the Pythagorean theorem. For more general lengths, we're going to do exactly like we did for more general areas, is we're going to approximate the curve by line segments and estimate, use more line segments, and take a limit. So you start with your curve over here. It looks like a parabola, and you're interested in finding the length of the curve between those 2 points, and so you approximate it by a certain number of secant lines, which are pretty good approximations, and that's not going to give you a bad approximation, but as you take more and more line segments using a smaller and smaller partition of the interval, you'll take a limit and you'll end up with an integral. And the formula that we get, so here I'm looking at the curve y equals f of x, say between some a value and some b, which is another x value. And the definition that we come up with is that the length of that curve is the integral from a to b of the square root of 1 plus f prime of x squared dx, or if you like, the integral from a to b of the square root of 1 plus y prime squared dx. And here inside in the integral, inside the radical, you see these 1 plus something squared. That's the same as 1 squared plus something squared, and that comes from looking at the distance formula for the small little secant lines. Now, in order for this integral to make any sense, we need to assume that the derivative function is continuous on the interval from a to b. And you can see the derivation on pages 538 to 539 of the text. Instead, I want to focus on doing an example. So I want to look at the curve y squared equals 4 times x plus 4 quantity cubed within the range of x between 0 and 2, and where the y values are all assumed to be positive. Now, because the y values are assumed to be positive, I can take the square root of my expression, and I find that y equals 2 times x plus 4 to the 3 halves. And I need to put that into my arc length formula, so I'm going to need to compute the derivative and then square the derivative, add 1, and take the square root. So we'll do a bunch of that work on the side here. So y prime is going to be the 2 times 3 halves x plus 4 to the 1 half, which is the same thing as 3 times x plus 4 to the 1 half. So 1 plus y prime squared will be 1 plus this quantity squared, so that's the same thing as 1 plus 9 times x plus 4, which is the same thing as 9x plus 37. So in our arc length formula, that's going to be the integral from 0 to 2 of the square root of 1 plus y prime squared dx. And we put in our expression for 1 plus y prime squared. This is the integral from 0 to 2 of the square root of 9x plus 37 dx. And I do recommend doing a lot of this scratch work over on the side to keep your work nice and clean. This also will help you to keep from making too many mistakes by breaking the process into a small number of easier steps. Now, we look at that integral, and the way that we would compute that is we are going to set u equal to the inside. You could do this by a rationalizing substitution, where you would use u equals the square root of 9x plus 37, but when you just have the square root of ax plus b as the thing you're trying to integrate, you can just have u be that linear expression, and we'll see how that works in a second. So du is 9 dx. When x equals 0, my u is going to be 9 times 0 plus 37, so 37. And when x equals 2, I'm changing my limits of integration. We're going to find that u equals 9 times 2 plus 37, which is 55. Put that into the integral, and we have that our arc length is the integral from 37 to 55 of the square root of u du. So that's u to the 1 half, which integrates rather nicely. So we have u to the 3 halves times 2/3 evaluated from, oops, and what did I miss? I missed 9 coming from my du, so I need a 1/9 outside of my integral to compensate for that. So I'll multiply my 2/3 times 1/9. and then we evaluate from 37 to 55. 1/9 times 2/3 doesn't cancel, so we get 2 over 27 times 55 to the 3/2 minus 37 to the 3/2. And if you like, that sort of simplifies to 2/27. 55 square root of 55 minus 37 square root of 37. And then we have units here because this is supposed to be a length. Okay. Examples, hold on, new page. For an example like this in the book, you can see example 1 on page 539. And there's a, just like with lots of the formulas we've seen, there's a version, so I gave the version when we have y equals f of x. If instead you have x given as a function of y, then the arc length is the integral from c to d, where c less than or equal to y less than or equal to d is my range of the square root of 1 plus g prime of y squared dy. And that, of course, assumes that g prime is continuous. And for some examples like that, you can see 2 and 3 in the textbook. The last thing that we want to talk about in this section is the arc length function. So this is where you set s of x equal to the length of the curve y equals f of x from the point a comma f of a to the point x comma f of x. Right, so those are 2 points on the curve. You've got a starting point and an ending point, and in that situation we just plug straight into our function that we had a second ago. So this is the integral from a to x of the square root of 1 plus f prime of t squared dt. Notice that I use t for my integration variable because the variable x is being used to describe my endpoint. Okay? So this is the so-called arc length function, and we'll give a computation of this on the next page in a second. One thing to note is that there's a useful fact for later. Because of the fundamental theorem of calculus, that if you take the derivative of this function, right, so I have a function that's defined in terms of an integral, and the fundamental theorem of calculus part 1 tells us how to take the derivative, and that's gotten by just taking the integrand function and plugging in the variable x. And this is something that'll be useful later, I promise. Good, so let's see an example of a computation of the arc length function. So I'm interested in looking at the function y equals ln of sine x with the restriction that x is between 0 and pi. Right, so this makes sure that the sine function is positive, so I have a function that I can actually take the logarithm of. And I want to find the arc length function with the starting point of pi over 2 comma 0. Right. So the function s of x, just writing it again from the previous page is the integral from the starting x value to x of the square root of 1 plus f prime of t squared dt. So I'm going to do a little bit of work on the side in order to simplify the expression 1 plus f prime of t squared. So my f of t is natural log of sine of t take the derivative of that, use the chain rule, so I get the cotangent of t for the derivative, and so when I square that and add 1, I have 1 plus cotangent squared of t, and if you remember your Pythagorean identities, hopefully this ends up being cosecant squared of t. So when I take the square root of that, we end up with cosecant squared t because, sorry, not cosecant squared, just cosecant, because I'm taking the square root. And the reason that that doesn't involve a plus or minus or a negative is because of our restriction when x is between 0 and pi. That tells us that cosecant of, sorry, that should be a t, cosecant of t, that's 1 over sine t, that's a positive number. Right? So when I take the square root of it, I just get cosecant back. Right. So now I'm going to take that expression for 1 plus f prime of t squared and put it into my integral. We have to remember the integral formula for the cosecant function. That's the natural log of the absolute value of the cosecant minus the cotangent. And we're evaluating that from pi over 2 to x. So we have ln absolute value of cosecant x minus cotangent x minus the natural log of absolute value of cosecant pi over 2 minus cotangent pi over 2. And let's remind ourselves, cosecant of pi over 2 is 1 over sine pi over 2. Sine of pi over 2 is 1. So here I get a 1. And then cotangent of pi over 2 is cosine over sine at pi over 2, which is going to be 0. So here, the second expression I have is ln of 1, which is 0. So we end up with our arc length function equaling ln absolute value cosecant x minus cotangent x. And you can see more examples like this in example 4 in the textbook. So that's the end of the lecture on section 8.1, arc lengths.